Okay, plotting in R. Okay, so if we go back, you can see we're in the training section and we have a link here from our homepage, and this will get you to the plotting in R. Oh, I just went backwards again. Cool. And so you can see this is passing all our checks, and hopefully you followed the instructions to get these specific packages for today. If not, you can quickly copy and paste this code into your R screen, R console, and that will get things installing for you. Cool. And so we have two presentations, like I talked about. We'll have the first presentation, which is about base plotting, and then we'll have the second presentation, which is about plotting with ggplot, which is it's a very cool tool. Okay, I'm just going to rearrange my screen real quick so that I can see the chat box. And like I said, we have plenty of time today, so I really encourage people to interrupt. There was lots of good interaction yesterday. Otherwise, I just feel like I'm talking into a void, and I feel lonely.
Lonely.
Cool. So here we go. So introduction to plotting. So what we talked about initially is yesterday is plotting is one of the real strong points of R. Okay. And so this is where you can really demonstrate your R skills and produce some plots that will make people really impressed with your data, and they'll be a lot better looking than what you can do in Excel. And so just as before, you can download the material for today from these links, and also the links in the homepage that we were just looking at. And you just orient yourself in exactly the same way. All the slides and everything are in the same position within the zip file. You just got to move to our course. Okay. So hopefully everyone has success with downloading and figuring out where they need to be. Okay, and so yeah, like I was saying, it's really one of the strong points of R is the plotting capabilities. I know a lot of people are very have a lot of affinity to Python. Python is a really nice language to use. However, its plotting is nowhere near as good as R. And then there's MATLAB, which again, they have a lot of really nice libraries for things like image analysis and other things. But again, the plotting is, I would say with both Python and MATLAB, it's really hard to make publication quality figures straight away. You would have to take them out and then do lots of manual alteration. While in R, you could create a publication ready figure pretty easily. You still might want to do some edits if you want, just for sizing and stuff like that, because that might be easier. But okay, yeah, we just got a question. Can't find the R course path. Could you please show again where to find it to set the working directory? Yes. So it's going to be wherever you downloaded it. Okay, so you'll download something, the file, and it's going to be a zip file. So then you need to unzip it. And then once it's unzipped, you can you'll want to set your working directory to be in that folder. So that'll be the path to the download. And then this will be whatever the folder is called that's unzipped. And then there should be something called R course. Okay, does that make sense? Is anyone else lost? I think the key step that I always forget to explain is you need to unzip it first. Cool. Okay, so okay, yeah, we've still got some people setting up. Well, if anyone has any issues and we need to stop and go back and make sure you're set up, that's all good. I'm just going to introduce some introduction about plotting and the theory of plotting in R. And when we get to the code bit, we can make sure everyone's on track. Okay, so there's three main packages or three main ways people do plotting in R. These are with the base graphics, the lattice package, and then ggplot2. Base graphics, its strength, but also its weakness is in the fact it uses a what was called a pen and paper model. And so when we talk about a pen and paper model for stuff like plotting, what we mean is once you've made a mark on the paper, you can't take it back. So this means as you plot, you can gradually build your figure. But if you add something to your plot that you don't like, or say you make your dots a shape that you don't want them to be, or something like that, you have to start again. In theory, if you're doing like good notebook practice, you're keeping the code that you're running in your script section, your top left-hand section of RStudio, then that should be fine. It's not too big a deal. But if some elements took a while to actually get them to plot, then it can be time-consuming. Lattice and ggplot2, on the other hand, they're built on this routines that mean they can be dynamically updated. It was first used here, explaining in cryptographics. But really, the main things you need to know is with ggplot, you can change like an aesthetic value, and it will dynamically update what you're looking at in the plot without rewriting it all from the beginning. Okay, and so as you can imagine, these two approaches, one is very useful and versatile, but it's also quite memory intensive, and it's quite like it's much harder for your computer to handle. And so if you are working with very, very large data sets, say you draw a scatter plot and you want to just compare gene expression in one condition versus gene expression in the other, you might have something like 10,000 data points. And so that is a lot of data points to be on a plot. And if you then want to do lots of editing of that, in ggplot with dynamic updating, then that can be quite hard going, and it can, depending on your data set, be easier just to use base R for it. Okay, so this is pretty much what I was talking about. Once it's plot, you can only add to it. Okay. It's harder to update. You really just normally have to refresh. But because of the way it's been doing, it's a lot faster. Okay. And this really shows in genomic data sets. Okay, so we're going to start by doing a demo, and we're going to walk through step by step how I might build up a scatter and line plot. And we're going to go into a lot of detail into this plot. And then after that, I'll show you some other types of plots. And most of them can be edited and features can be added in much the same way. But most of the time, you're going to be looking at scatter and line plots, I feel. Okay. So before we get started with the code, I just want to check everyone's been able to download what they need to download and have been able to orient themselves in the right place. If you haven't, speak now, and we can just give you a chance to get on the same page as us.
Sorry, in the folder that I just downloaded from the plotting in R, is there a subdirectory specifically that we should assign as our working directory?
Yeah, the one R course, R_course.
Course. Got it. Thank you.
Yeah, yep. Yeah. And so for every course we run, all the material, every time we want you to go to R course. Okay, so it'll be a consistent rule for you. So we have a question: is Viridis? So I'm guessing, is Viridis the same as Viridis Lite? That's the question. We will touch on Viridis a little bit later on. They are slightly different packages, as you can probably tell by the naming of it. Viridis Lite, I believe, just is a little bit more lightweight, so there's less stuff in it. Your BIOS manager is only downloading Viridis Lite. Okay, so did you try and install Viridis, and it's now installing Viridis Lite instead?
Yeah, every time when I try to download the Viridis, the only thing that is downloaded is this Viridis Lite. I don't know if something with the version of my BIOS manager, I don't know.
So I had, for a few of the packages where just copying and pasting the code to install didn't work, including for Viridis Lite, and so but I had success using the GUI to install the packages.
Okay, so I can quickly show the GUI. So you used RStudio, I'm assuming.
Yep.
And so you can go, let me share screen for Mariana. So you can go to, actually you can't see my toolbar, I don't think. So this won't be super helpful. Let me share screen in a different way. Here we go. So you'll get to see everything. So if we go up to tools, install packages, now you can start to install packages here through the GUI. Sometimes this works better. It works in a slightly different routines. And you can also try install.packages as well instead of BIOS manager install. BIOS manager is the installation program for Bioconductor. And generally it has a better routine. It's more rigorous for installation. And so that helps you make sure you get a working, correctly versioned package. Some of the times though, it's a bit too much of an overkill, and maybe you're not getting the right package as a result of that. Cool, so we're back in business. Okay, great. So yeah, we'll touch on Viridis in a little bit as well. So that's good you have it, because Viridis is a cool package. Okay, so first what we're going to do is just create a simple numeric vector, and this is just going to be our data points that we're going to plot. Okay, and so you can imagine we could do exactly the same thing, but getting data from an Excel spreadsheet or something like that you read in using Rio, right? So you could do Rio import, get the Excel spreadsheet, and then you can create a vector from that and call it treatment. But here we're just going to use a very dummy example with 5, 6 data points. Okay, so we're saving it as a variable treatment. And then we can just use the function called plot on treatment, and it will produce a plot. Okay, and so here it's like what plot does is it infers a lot of things about the data, and it makes its best guess as to what you want to be plotted. As you've given it one-dimensional data, it's assuming that on your y-axis you're going to have the actual values, and on the x-axis is going to be a simple counter of position 1, position 2, position 3. Okay, and so you can see that we have a nice little curve here. Okay, it also assumes that what you want to see is a scatter plot. Okay, so that's the default. Depending on your data types, it will plot different things, and we'll see a little bit of that later on. And you'll see that as you try and put different types of data into plot, whether it's a matrix or whether it's lists, things like that. Depending on the structure, it will do its best. Okay, so when we start to customize, we can add very simple options that will change the way the plots look. So if you do plot treatment, but this time we add the argument type, and then we say the type we want is an O. What happens is we get a line plot, but this time it's also overlaid with the dots as well. So you get both the best of both worlds, a line plot and a scatter. And it's a key thing with this is the expected argument here is a character. So you can't just put an O in. You have to put an O surrounded by quote marks. And so then you can also, there's lots of different types. You can also specify if you just want a line plot, or if you wanted to actually encode the yeah, and if you wanted to directly encode that you wanted a points plot, then you can do that with a P. So we have a question: where can we find those tricks, cheat sheets? So by tricks, I don't know. Did I say tricks? So by tricks, I guess, and cheat sheets.
No, not tricks. Sorry, not tricks, but okay, yeah, you have it now with dots and line. Well, I want it with triangles and lines, or.
Okay, yeah. So at the moment, what we're showing you is the defaults. Okay, and if you want to change some of these aesthetics, I'll show you how to customize that further in a little bit. If you wanted to say, so what this is doing, right, is it's saying I want a line plot, or I want points, okay, or I want a combination of the both. What you can then do on top of this is customize what these lines look like or what these points look like, which I think is getting to what you were asking, Javier. So if you wanted a triangle or you wanted a dashed line, these are further arguments that aren't type.
Yeah, but even a line or just a dot, you know what it is, but I have absolutely no idea. Where can I learn, or where is I don't know, a list of the different types of plots that we can design, or what is the command for each of these?
Yeah, so that we're going to go through that a little bit today, and I'll also add, there will be some links later on to some plotting options. I believe I have a cheat sheet link in here. You can also use question mark plot as well. So that gives you a complete list of the types with question mark plot. So anytime you're doing a function, you can do question mark and it will take you to the help page. And so we can have a look at that now. Okay. Just going to put us into applying it now. Yep. Okay, so then you'll get this. So this happens when you get an ambiguity about where this function is from. Okay. And so you'll often get this, say, a common one is Rio, right? So we used a function yesterday called import and export. And so these are really common function names. So if you load in two packages that both use an import and export function, then when you look up for help, it's not going to know which one you're looking for. And so at the moment, we're just interested in XY plotting and base. Okay, so it tells you which package it's from. We're just interested in base for the moment. Okay, and so you can see here, here it has a detailed list of what types you can use, right? And so you've got points, lines, both. All kinds, histograms, stair steps. Okay, and then it has more information on the other arguments that you can use. And then it has some examples. Okay, so this is always a good first step, but this is really only telling you about the basics of type. There is a lot of other graphical parameters that are here. Okay, and we're going to get into some of these in more detail. So yeah, we're going to get into more details, but you can see there's lots of ways we can customize going on. Like, I'm not going into showing you what's in all of these, but these are all arguments that you can add to alter what it looks like. Okay, so it's very extensive, the customization you can do. That said, I normally stick to about 5 different things that I might play with, and I'm going to be showing you those ones, which are the ones that I think are the most important. Okay. Okay, so one of these things that you might want to add is the main argument. Okay, so main basically is your header. What are you titling your plot? And so in this, I'm keeping it very simple. I'm just calling it my plot, and you get a header up here. You can also add a subtitle if you want, and that will appear down here at the bottom. You may also want to update what your x-axis is labeled and your y-axis is labeled. And so you can use the arguments xlab and ylab for this. And so this is fairly straightforward, right? It makes sense. Xlab, ylab, and you can see it's updating positions here. So we could, in theory, do both of these, right? We could do these labels, and then we could also do these, and everything would be correctly labeled. You can then control the orientation of labels using LAS. LAS accepts a number, and the number corresponds to which axis you're talking about. So if you look here, by default, the y-axis is plotted in an orientation which isn't the easiest to read. And so typically what I do is I add LAS equals 1, and this will rotate your y-axis. Okay, but you can also do it to the x-axis if you want, but this is less intuitive, I think. You can do it to both as well if you combine these in a vector. Okay, so with that is most of the labeling that you'd want to do to the plot. The next thing that quite often you want to do is if you have points that you want to alter the size. So you can use CEX equals 2 or CEX equals 0.5, right? And you can see how it makes the dots much smaller or much bigger. And so for a lot of these, the default size is 1, so it's nice and easy. And so you can make very slight alterations to make it easier to interpret what the data points look like. Quite often when you're plotting thousands of data points, like with a genomic data set, you'll actually want to make it very small. Otherwise, the entire plot will just be points and you won't be able to see anything. And so then this starts to get to what we talked about earlier. Say you want to make your dots, you want to turn them into triangles, or you want to turn them into squares, or you want them filled or not filled. this is the point character parameter or patch. And so there's lots of different options for these. Do I have a link? No. Okay. So this is actually what I do a lot of the time. If I want to do, I think this one's pretty good. Anytime I have a parameter, I'm not 100% sure which one I want to use. I just Google it. Okay, and so the patch options are here. And so I could put 1 in, which is the default, which is a nice empty circle. But there's lots of other options to choose between. This isn't controlling their color or anything, it's just controlling their shape. So we updated patch 1 to patch 20, so we can look at that. And all this is a slightly smaller but filled circle. If we're working with lines, the main things you can do with lines is change the pattern of the lines and change the thickness. So the thickness is controlled by the line weight density, which is LWD. So we can make that a 10 to make it really thick, or 0.5 to make it really thin. Again, 1 is the default. And then LTY will control the pattern. Okay, so we can also similarly look up LTY. Oh, my internet's being slow now. Okay, and so I often come to this website specifically for plotting parameters, and you can see there's several different options. And so you can do this. I'll either go to a website and look for a specific one I want, or I'll just keep trying. I'll try 1, I'll try 2, I'll try 3, and I'll find the one that I like the most. So here we're looking at just the basic, and then we're also looking at a nice dashed 1 and 2. Okay. So now we get to color. Okay, and so to add color to any of these, you just use the argument col. Okay, and this is a standard argument that you'll see in many different packages. But for plotting, this is what we use. And you can give it any color pretty much. There's lots of different options for colors. So we can have the basics like red, blue, or whatever, but then there's variants of all of these as well. So here's a Dodger blue, which is a nice lighter blue. And again, you can search for our color names, codes. You can also use hex codes here, for those of you familiar with hex codes. So that means you can go to a palette picker and pick out a hex code. And so we can actually look at a chart here. Okay, and so these are the common colors in R. Just lots of different options, lots of different grays, and they all have different names, okay? But like I said, you could also go to you go to something like this, and then you can play it. There's lots of interfaces that do this, and so it's about finding the one that you like the most. But here you can hit space for a new palette. So you could look around, find a palette you like, and then you could use these colors. And it's just a case of copying this. And we could go into here and go plot. treatment col equals. Okay, I'm going to quickly switch the screen so you can actually see what I'm doing. Okay, and so now I have this nice pastel. Okay, so you can see it's super easy to customize it to exactly what you want.
Didn't you need to write type L inside the argument?
Pardon?
The other plot functions used type L before saying the color.
Ah, yeah. So if you remember, yeah, we can look back into this. Let me get this back up. So it depends on what. So if we remember, when you do a function, okay, you can. I could do this. Let me grab up this plot. We'll look at plot. You can see the orders of the arguments going into plot. Okay. And when you look at the orders, it's expecting in the first slot for the x coordinates and potentially in the second slot some y coordinates. Okay. Because there is no, if we were looking at something like, I think, let me explain with the one that we looked at yesterday, dir. Okay. So dir, it has a specific order of arguments, right? So when you have dir, it's expecting the first argument to be path, the second one to be a pattern, the third one to be whether you want all the files, okay? And so if I just do dir by itself, it figures it out because there's defaults. Okay, so all of these have default values. Now, if I was to try and say I want just the YAML files, okay? So I want the pattern to be YAML. That doesn't work because it needs to know which argument it is. Okay, but if I remove this and I provide the first argument first, which is I'm looking in this current directory, and then I say I want to find YAMLs, it finds it. So what this means is there's a specific order, and the order only matters if you are not providing the name. But if I provide the name and tell it this argument is a pattern, then it doesn't matter what order they're in. Okay, so the order only matters here, right? Because I'm not providing the name of the argument. And that's why it doesn't work up here. So if we get back to our plotting example, we can add in type equals L, and it'll do a line plot. I can also do type equals L, and it still works the same. Or I could do type equals P, and then I could have patch at the end. And let's say we're going to do 16. Okay. And so because I'm providing the names of these, the ordering doesn't matter for these ones. The one that does matter is treatment, because I haven't given this a name. I'm not saying X is equal to treatment. I think if in theory, I haven't tried this out, but if I did X equals treatment at the end, yeah, it plots fine. Okay, so the order only matters if the arguments haven't been named. Okay, and by named, I mean assigned by saying X equals or whatever.
Thanks, but you can skip writing type at all because there's a default, because the default is L.
Yeah, exactly. Exactly. If there isn't a default in a function, it will error. If there isn't a default and you don't include it in the function, it will error out and it will tell you there is no value, default value for whatever that argument is. It needs a entry included.
Great, thank you.
Yeah, so R does its best to fill in the gaps, but if there's nothing that is specified, it will fail, and it will let you know why. Okay, so digging into other parameters, I showed you question mark plot. There's also question mark par. We also dug into question mark par through the link that we went to when we went to the help page in plot. So between these two, these shows you all of the different types of plots that you can do with base and the parameters that you can apply to these. Okay, so hopefully you can see you can do a ton of customization of just the aesthetics to make it conducive to really showing the story that you want to tell with the data. In reality, we're not typically showing just a plot like this most of the time. We're showing many data points next to each other and comparing between groups. And so what you actually want to be able to do is plot vectors against each other, or plot more than one vector at once. And so a common thing you might do is add in, say, a control. So now we have control and we have treatment. And if you plot them next to each other like this, if you remember when we looked at question mark plot, it's expecting an X and a Y argument. You can drop the Y argument, but you need at least an X. But if you provide a Y argument, it will use that to make a XY scatter plot. And so you can see that here. This is the product of that. We have the X against the Y, treatment against control. Okay. And you can also see that, I think I didn't mention it here, but you can see that treatment is inherited here and control and treatment are inherited here. So your object names can actually be quite, or the variable names for your objects can be important because they can save you a job later on when you start to plot them. So if you use sensible names, it means you won't have to rename everything later on when you're making the plots. And so this is nice if you want to do an XY plot, but quite often we're comparing, again, control versus treatment over, say, a time series. And so they might have the same x-axis, and you want to compare the two groups in Y. And so you'll need two different lines. And so when you do this, the way to do it is actually you create a plot and then you add lines to it with a separate function. And so this really gets into this idea of a pen and paper model, right? You're going to create this plot. It's going to create all the dimensions of the plot. And then you're going to add to that plot afterwards. And so you can start to see some of the issues with this. And the issues with the fact it doesn't dynamically update itself. And so here we plot the treatment. We're giving a blue color. And then we're also using the function lines to add another line. We can still use the type argument because in this case we want a line, but we also want the points. And then we're going to use some of these customization options to actually make it easier to tell which is the difference between them. So we have our patch, LTY, and col. Okay. And so that's going to make it really easy to tell which one is which, because one is dashed, one is squares, etc., etc. Now what you can see is that our control actually has a higher range than our treatment. And because the plot was established with our treatment, it doesn't actually update to include space for this additional line up here. Okay, so I'm just inferring from the trend that this is going to go up here because this is actually a simple XY. And so there's another data point somewhere up here that we can't see because it's outside of the parameters of the plot. The margins are blocking it off. So this is an issue, right? Because you're missing a data point. So we can control that by changing the limits of the plot, okay? Actually, well, there's two ways to get around this. I've used both. So one way is when you realize this, you just plot control first, and it will plot the ranges of control, and then you plot treatment afterwards, and it would work fine. However, having a more fine-tuned control is a much better way to go. And so what we have here is we have our control, and we know that the control goes up to 100. Okay, so you can just look at your data. If you remember, there's a function called max, so you can use max to check how high does my control go. And then you can alter one of the arguments of either ylim or xlim, depending on which limits are needed to be updated. So in this case, it's the y-axis that's too small. And so you can say ylim, and then you provide a vector, a numeric vector, which contains the lower limit and the top limit. So in this case, we want it still to be the lower limit to be 0 and the top limit to be 100. Okay. So the defaults for this are assigned based on your original data that goes into your plot. Okay. So in this case, it will be based off of treatment. And treatment doesn't have a higher range. If we remember, I just scoot back to see when we define treatment. It goes up to 80. Okay, so it'll add, I can't remember how much it adds. It's something like 10% onto the top limit. And it will use that in the defaults. But we need to overwrite that because it's not enough for our control. So we're adding it up to 100. Okay, and so now you can see we have 100 and it looks nice. We get all of our points on the data plot. And so it looks good. Okay. So I talked about how to kind of do this, to intuit how much your data is. But if you start to build functions to make plots that are reoccurring, or you're going to do this to lots and lots of different data sets, and you just want to be able to copy and paste and not have to alter depending on what the data looks like, you can actually start to use some of the functions that we've talked about in the past to actually dynamically update what you want the limits to be. And so there's a function called range. And so you can do range on the data set, and this will calculate what the top and bottom most values are in your data set. And so you just give it some numbers and it will calculate that. So what we're doing here is we're using the range function. We are saying we definitely want the bottom to be 0, okay? But we also give it treatment and we give it control. Okay, so it's going to look through all these vectors and it's going to find out that the topmost value, which we know is 100 because it's in control, we looked at it before, and it will get the bottommost value, which will be 0, unless these contained a negative, which we know they don't. And so that means with this function, we're automatically detecting what is the top and the bottom limit of our data set. So if in the future you updated treatment and control, it would update the limits for you. And so then we can use ylim equals grange. Okay. So I'm just going to get a little more water. You can hopefully see that something else has happened to this plot. We haven't just added a dynamically updating So we have this function determining range, and that's being fitted into added into ylim. But you can also see we've added in these two other arguments. Axes equals false and an equals false. Okay. And now we look at our plot and it just looks very bare. And so this shows you how you can really get into the customization of your plot, because every single aspect of the plot is tunable and controllable, and you just have to turn it off and then you can add them back in. So to turn off the axes, you can say axes equals false, and to turn off the annotation, you say annotation equals false. And so then when you do this, you have very little apart from your curve. But what we can do is then build it back up in the exact way that we want it to be to look like. And so we do this by using the function's axis. Okay, so this will be adding the axes back in, and you'll do one axis at a time. So first up, we're going to do the x-axis, and so the axis function has several key arguments in it. The first one is side, so this determines where you're adding an axis. So you can also use this if you wanted to, for example, change where the axes were. If you wanted actually an axis at the top and an axis on the right-hand side, you could do it this way as well. Side 1 equals x. I just think side 2 is here. And then 3, 4, I believe, but I could be wrong. But you can always just check it online. And so once you specify the side, you then say, where do you want the labels? Okay, and that's with at. So we want our labels at positions 1, 2, 3, 4, 5, 6. Okay, and then you decide what the labels will be. So in this case, we have the 3-letter days of the weeks. And so this data set is actually starting to make a little bit more sense now, because we actually have good labeling of the x-axis. Okay, before we just had 1 through 6. The next one we're going to do is we do the y-axis. And so we can use axis. We say we want the side number 2. So that means we're going to be working on the y-axis. And then we're going to say LAS equals 1. So that means it's rotated. This is generally seen as good practice for figures because it's much more humanly readable. Most of the time you don't want to read like this. And then you say, where do you want it? Okay. And so we're using the seek function, which we met yesterday. And we're saying we want to go from seek from 0 to grange 2. Okay, so if we go back and look at grange, the grange is anytime you use the range function, it produces a vector that is the length of 2. The first point will be the lower limit, and the second point will be the higher limit. So this is where our 100 is. So we're saying we want 0 to 100, and we want it by 20. And so here we're not adding labels. So here we specifically added labels. And because we're not adding labels, it will just use numbers instead. Okay, so we don't have any specific character labels we want to add because this is a quantitative measure. So we can just decide where we want the ticks to be, essentially, and that will be it. And so this is nice because you can control exactly how many different ticks that you see on the axis, where they are, make sure they make sense. Sometimes the default amount would break things into 2.5 and 3.5 and things like that. And when you do that, it can be annoying because your data might not be possible to have a half value or a full or a quarter value. And so representing that in the graph just might not make intuitive sense. So you can control things this way. Okay, so we just got a good question. Isn't it simpler to use the max function instead of range? It depends what you're going to do with it. Okay, so one thing you'll notice with coding like this is there are so many different ways of doing the same thing. And the way you might originally do it, like a week later, you might find a more efficient way of doing it. And then a week later, you might find that the original way is more efficient if you do it in a slightly different way. There's so many different ways to do things. And so using max would be a suitable way of doing this. Okay, and so just to explain, so if we go here, we can use max, and we could do max on treatment and control. Let me just copy this. Okay. Let's go into R. Okay. So we have our G range. That looks good. So the alternative really is we're basically trying to find this 100 value, and we want a vector. So we could just do, say, oh, I turned on Siri. Nope. If you max, we wouldn't need the 0. And if we did this, this would give us the 100. But then we wouldn't also have the 0. So we'd then have to do okay. And that would give us the G range of 0 to 100. It would be exactly the same now. Why do we need the 0? Well, if you're defining limits, remember with the plot, then you'll need the 0. So when we do this, we can do y lim equals G range, right? And we just altered that. You have to have the 0 for that. And so both of these work very well for that. Obviously, for what we're doing now, when we're redefining the axes here, okay, you only need the max value. And so if you were just doing this, you wouldn't necessarily need to be able to get the 0 as well. But because you're defining the limits with the 0, it's easier just to, you have this vector already. It's easier just to grab the second rather than have to do max again. But if we look at this, they're kind of very similar efficiencies, right? It's just one, you have a slightly different function, and you're using, here we're using two functions and one function, but that is pretty much about the same. Yeah. So this is definitely an alternative, right? Is you can use max and min and max separately. Range is just kind of a way to get both at the same time. This definitely works, and I definitely wouldn't say it's wrong. I would say that this option totally works. It's just a little bit more complicated. Okay, and so that's for people who aren't looking at the chat. I'm just going to quickly copy it in here. There we go. Okay, so here for people who weren't all over the chat, we have the y lim being a set here, and we're setting it first with min and with max. Okay, so this would be the same, have the same effect as range, right? The one big thing about this that I would say is, this works totally fine because within our data we have a 0. Okay, and so this is a 0 point. Most of the time you'll want your plots to start, or like, no, it depends what you're trying to plot, but a lot of the times you want your plots to start at 0. So if I went to say, treatment, and I did 1 to 2, and I made them instead, let's say 5 and 10. Okay, you can see what treatment looks like now because I just did an update. And now if we did this, oh, because treatment and control. Yeah. So if I just did, got rid of control. Okay, there you go. There's your example. So in this case, I'm basing it purely on our treatment data set. Our treatment doesn't have a 0 in it. And you can see we're no longer rooted to 0 in the axis. So that's, it's not an issue. It just is less clear. And a lot of the time, if you're making a figure that you want to present, you're going to rescale this to get it to 0 because it will look better. But yeah, like this is, like I was saying, this is a totally valid way of doing things. There are just so many different ways to get to the same ending. So a lot of the times when if you go into the exercises, we will show you a way to do things. It's 9 times out of 10, it's not the only way to do it. Okay. So one of the last things that you can add back in is the box. Okay. Some people really like the boxes. So this is a way to get them back. I personally hate the boxes, so I would never encourage anyone to do this. I come from the school of thought of when you're plotting, much less is more, and the less things that you can have on the plot, the better. So here is the function. You may use it. It is up to you and your aesthetics, but I don't think I don't endorse it. Okay. So you can see how in a few steps, right, we've gone from this, which has nothing, and we've rebuilt the plot exactly in our image, how we want it to be, how we want it to look like, and it's essentially regenerated the plot that we had at the beginning, but with some slightly updated aesthetics to fit better. We can then add in our control data using the lines argument. And so now everything fits, it looks nice. And then we need to start labeling it. Okay, so at this point, we have all the data there, it all fits. Most of the labels for the actual data itself are good, but we need to actually get some like x-axis labels, some y-axis labels, some titles, and legend. Okay, so the legend argument allows you to add a legend to a plot. And so, wait, it's not an argument, it's a function. So you have legend, and you can just control where it will be using top left, top right, bottom left, bottom right. Within the function, there is an argument for legend, and this is basically what do you want to name your data series. Okay. Then you can show what color is attributed to them, if they have differences in the point character and the line type. Okay. So you basically use the values that you've used already. And so then you can see here, we produce this nice legend that labels what we're doing. And so I think with this, we did a really good job of redundancy in showing the difference between the two data series. It's really important to have redundancy because different people have different abilities to see. And so having both different like shapes, different colors, and different line types will help people differentiate. And you can go even further if you wanted to and change the line width as well. I think that's pretty much all the characteristics you can change to differentiate between the two data series. And so if you were to put this all together, this is what this would look like, okay? So this is our full plot. So we do all of this, and this comes into 1, 2, 3, 4, 5, 6 lines of code. And each bit is added in a very stepwise manner. So that kind of explains how plotting like this works, and how I think after seeing this kind of stepwise way we've added things, hopefully you can understand what the pen and paper model means and how base plotting works. And perhaps why it is less memory intensive, because all it's doing is going, I'm doing this, it does it, and then it doesn't have to think about it anymore. It's already, the data's there, it's plotted it, and it's just saved at that point. Okay, so as I mentioned a couple of slides ago, it's really important for people to be actually able to differentiate your different points and your different data series. And so this is where packages that we also talked about earlier, like Viridis, come in. And so a large proportion of people in even today's audience potentially could be colorblind, right? And especially considering who goes to science talks and the demographics in science at the moment, white males are the group that have more colorblindness than any other group. So that's 1 in 10 people. So that you pretty much at any meeting you go to, you're going to have someone who maybe struggles with colors. And traditionally, science has not done a great job at picking colors that are good for people to see. So if you remember, anyone's looked at microarrays, red and green is commonly used there, and they were very, very tough to tell the difference between them for certain types of people with color blindness. So R has ways to deal with this. There are these packages called palette packages that have curated collections of colors. Okay, and these could be literally, they don't have to be helping with things like color blindness. They can be for anything from stuff like LaCroix flavors to different types of Pokemon. And there's a large list you can find here, like different fan groups or whatever you want to do. And I did a lot of my thesis when I did my PhD. I used Wes Anderson colors for a lot of my R plots that I did in that. And so these palettes exist to help you choose colors that fit a certain aesthetic and style that you want to convey with your data. One of these palettes, though, that is the most useful is Viridis, because it has these colors that are curated and grouped together based on their ability to be differentiated. And so the way that a palette works is you just install them, just like any other. You do install.packages, or you can do BIOS manager install, or you can use the GUI. You then load it in with the library. And then you should just have a single function in it, which will give you hex codes. So in this case, I can say Viridis, and I say I want to have 5 different colors. So I do Viridis, a function, I put 5 in, and I'll get the hex code of 5 of these. Okay. And the other couple are hidden behind this plot, but this shows you what these colors would look like. So it's quite tealy through to yellow. There's purple through yellow spectrum. And most of these palettes will have several spectrum options that you can choose between to decide which ones you like the best. And so you might have been able to tell I'm quite opinionated about data visualization, and I think a really good resource to get good at data visualization is this textbook here. It's an online textbook, so you can have a look. A lot is just about the theory of what good data visualization is. Is it following these points where it's easy to understand, it's very accessible? Is it actually engaging and like attractive? Does it contain the information you need without additional information? And this is something as scientists, I think a lot of people struggle with. They want to add as much as they can because it's your baby, it's your work. You've worked really hard to make something and you want to show as much as you can. But often that could detract from the main point or the main story. And then, is this the best plot to tell the story I want to tell? And that's a really hard thing to do, especially when you're getting started and you don't know as much about data visualization. Okay, so at this point, I'm going to do another poll. Okay, so I'll give you a minute to do this. It's another which are true. Okay, let's end that poll there. Oh, and we got a few last minute entries. Okay, let's share the results. Okay, so I think the general consensus is everyone is broadly in the right line. So yeah, we can use the lines function to add additional series. LAS was the function we used, or the argument to change orientation. It isn't easy to take something away once you've added it to a plot, and that's the whole pen and paper model, right? You can re-graph it, start again at the beginning, which can be relatively straightforward, but it depends on what you're plotting. And yeah, your axes are predetermined by your input data. However, I showed you a way that you can delete the axes and then rebuild them up from the ground. So I think the majority of people got those, the 3 of the 4 right as true. It's a good job. Okay, so now that I've kind of gone through the majority of what we do with base plots and how to build up the aesthetics and the parameters, I'm going to show you kind of go through a tour of some of the other basic plotting functions. There are functions that aren't just plot. And if any of the arguments differ in these functions, I'll try and highlight them. And then once we do that, we'll talk about saving plots briefly. Okay. So first off, we're going to start with the bar plot. So there is a built-in function called bar plot for bar plots. It handles plots in a slightly different way to just regular plot. And so we can just hand it our numeric vector again. So this is our treatment, and it will just produce a nice bar plot like this. In much the same way as we did for the dot plot. We can add names to the x-axis, but it uses a slightly different input for the names. It uses an argument called names.arg. And so it's just a slight difference in the way that bar plot works versus plot. Okay, and this is really because the x-axis is expecting categories, and the y-axis is expecting it to be numeric, and so it doesn't have as much flexibility as, say, a scatter plot or something like that. You can, however, if you name your object beforehand, it will just infer the names from your object. So in this case, we're using the names function to update the treatment vector. Okay, so this is not affecting, and this isn't affecting or directing plotting in any way at this step. And we're just adding names to this vector. But then once it gets added into, once we actually use that named vector in bar plot, it can then use these names in the x-axis here. Sometimes you'll want several, there's like other forms of bar plot, right, where you have several data series and you might have them next to each other, or you might have them stacked. And so bar plot can handle that pretty well as well. And so to be able to do that, you'll need to read in this example data set, for example, plot.txt. And so if you're in the right place, you'll just be able to copy and paste this command, and it will get you the data loaded in. Okay, it's just through this path. So typically, bar plot is expecting your data to be a matrix. Okay, and so to be able to do that, it means we need to do some coercion, because when you do read.table, it's going to read it in as a data frame. And so to do that, we can use the coercion functions that we met yesterday for the as dot. And so whenever you use these, it's going to be as dot whatever data type you want to end up with. So in this case, we want a matrix, so we just say as dot matrix, and it'll turn the data we just read in from a data frame into a matrix, and then bar plot can read it in. It's going to recognize the fact that there's several data series, and it will stack them accordingly. Okay, so in this case, we have a treatment and we have a control. We read in the header associated with this. I can show you it. I might show you what the data looks like real quick. Yours is just called example. Okay, let's have a quick look. There is an example and there is an example plot. So hopefully you should be reading an example plot. Let me check to see if example is the same. Yeah, they're exactly the same, so it doesn't matter which one you use. Cool. And so you can see that this is a data frame. It has the call names associated with it, and we can just do as.matrix data. And it doesn't look any different, but now bar plot is going to know what to do with it because it is a matrix, and then you'll get the same plot that we got. Okay, so yeah, this is how you get a stacked. It defaults to a stacked plot, but you can add the argument beside equals true. And then If you want to get real fancy with this, right, you're going to want to be able to label what each of these are and add colors to make it easier to differentiate rather than just grayscale. So we can say, oh, we're gonna add a title using main, right? So this is the same arguments we used before. We're gonna add a ylab. So we have a label on the y-axis. We still want besides equals true. And then we want the colors to come from Viridis. Okay, and so that's where we get this nice 6 colors here because we have 6 data points. Then we'll add a legend. It's going to be Monday through Saturday. I changed the size a little bit to make it smaller. And then the fill is Viridis. So that's how we know which each of these are.
If those are 2 separate calls to Viridis, will it always get the same 6 first, or?
Yeah. Yeah, so the way Viridis works is it's basically a spectrum of colors, okay? Going from all the way at one end to all the way at the other end, where one is very, very yellow and one is very, like this very dark purple. And it just cuts it exactly into 6 points, like equally spaced. Okay, so it's always going to be the same cut points when you do 6. And then when you do 7, it will be moved in even more. And so when you get up to a point where you're doing something like 20 colors, the difference between color 19 and color 18 might be quite small. But the difference between 20 and 1 will be about the same. Hope that makes sense.
Thank you.
Cool. Okay, so that's your bar plots. And we have histograms. Yeah, you can invert it. I think if you use I think it's rev. So let's just copy this and go into R. Okay, I'm gonna plot this. Oh, I need to load in Viridis first. And then let's draw it as it is. And I think if we do, I think it's rev. Yeah, it's rev. So if you use rev, that reverses a vector. And so you can see the difference between the two. The other nice thing about RStudio, right, is every time you iterate through these plots, you can just use this to navigate between them. So you can see the difference here. Cool. Okay, histograms. Okay, okay, so the question is there a way to load packages automatically into R when you get into R so you don't have to upload them every time? Okay, so there's several ways to do this in RStudio. That you can change your R configuration so that you have certain files uploaded in the startup. You can also, if you have, so let me switch back. So when I exit, I don't know if you can see this. Let me share everything, make sure you can see it. So I just press exit to quit my R session. And so what it's doing now is it's asking, shall I save a workspace image? So this is, I'd say, the better, rather than updating config files and stuff like that, because you never know what project you're going to work on, there's some packages you don't want to load in every time. Like most packages, you don't want to load in every time because you might be doing quite different things. However, if you're working on a project and it's a coherent project that you're working on regularly, what you can do is save something called a .rdata object. And what this does is it saves your environment. And so what I mean by that is that every package you've loaded in, every variable you've created, that's saved. And so that means the next time you come back to your R session, you can just load in this R data object and save your environment, and it will start up from where you left it. And so that means all your libraries will be loaded in. So when you're working on a project, that's a nice way to manage it, because you don't lose progress and you won't have to keep loading stuff in. There are other ways to manage systems like this as well, but I'd say it's really not that. Once you get into, tomorrow we'll talk a little bit about R Markdown. Once you start coding like that, I just put all of the libraries that I'm going to load into what are called a chunk, and then you can just press one button and it'll load all of them in at the start. So it's not too arduous. Okay, so histograms. So histograms, yeah, work in much the same way. There is a hist function. You just give it your data and it's going to create a histogram of your data. Okay. You can do things like add color in much the same way, change the limits. And here we're changing the CEX of the main. Okay, so if you remember, CEX controls size. A lot of these arguments have sub-arguments. So CEX main is just controlling the size of the main. So that's our label, histogram of treatment. Hist by default always does a main, okay, and it will just say histogram of whatever the vector that you put in is called. So the big thing to know with histograms is breaks, okay? So breaks controls how many buckets you're going to put your data into. And so with a histogram, right, it's all about how many different bins that you're using to pull your data. And so it will infer what it thinks is a good number here. So it's inferred that 4 looks about right. And it probably is, because if you do 2, for example, then you just have 2 bins and they're like equal size and it doesn't tell you much. But then if you go much higher to like 10, you have a lot of empty data points. So breaks is the really important one. It does generally do a good job with its guess, but you can control it manually depending on how you want the data to look. Okay, dot charts. This is the one I don't use very much because I don't work with data like this that often. But I think quite often in clinical studies, people like to do plots like this. And it's really good for paired data. And so what you can see here is we have, it's kind of squidged a little bit because of spacing. But essentially we have control and treatment on a Monday. And then we have control and treatment on a Tuesday, control and treatment on a Wednesday. So you can see the progression and the progression relative to each other and how control kind of accelerates ahead while treatment lags behind. To do this, you have to transpose the matrix first. It's expecting a very specific orientation. And so what transposing is doing, we can quickly look. Let's look at data, and then we do transpose of data. It just flips it around. And so it's expecting data in this format. Okay. And so your pairs will be essentially on the in the rows, and then the different groups across the columns. Again, you can use a lot of the same customizations that we've used before. So in this case, we're adding a main, we're adding some color, and we're using CEX to change the size of everything so that the plot fits and you can actually read it. Okay, so the final plot type we'll look at is box plots. And so that gives you a nice box and whisker, and you can see the quartile ranges. Okay, so For this, you'll just have to read in some slightly different data. For box plots, you'll want quite big data. So we have some gene expression data here, and it's under gene_data.txt. And so then we can just put that into the box plot function. Okay. And then you might also want to, like, quite often expression data looks like this, where you can just see essentially it's quite, it's not linear in its scaling. You have some genes that are expressed a ton, and then most genes expressed some. So you'll just be able to see, because of the scaling, the genes that are expressed a ton. So we often do like a log2 transformation. So we just use the log2 function on the expression data set. And then we just add some labels, we add some colors, and boxplot infers the rest. Okay. And so the data set we read in was just essentially a data frame. All the columns are the data. And then we have some row names. And again, it's inferring the groups from the column headers. Okay. I'm just gonna get some water. Okay, so we'd often want to actually combine plots. Obviously, when you're building figures and panels, you might want to, you'll often want to be able to do this in, I think a lot of people use PowerPoint, but generally better is like Illustrator or Inkscape. So you can arrange figures and they can look nice. But sometimes you'll just want to be able to create them in R. Say you have some very small plots and you want to compare 12 different conditions to each other. You can just create an array of plots really, really quickly and export them to a PDF so you can have a look at them. And so you can control like layout of plots using either the par function or the layout function. So in this case, we're going to use par. This is one of the parameters. We'll use the argument mfrow, and we'll supply it a vector. Okay, and this vector is going to give the dimensions of the plots that you want to produce. And by dimensions is how many plots. Okay, so we're going to update this to be a 2, 2, 2. So this is 2 rows, 2 columns. And so we can take this expression data that we just had, and we can plot a histogram of its distribution, see what it looks like. And so we update the parameters, then we say histogram, then we say histogram again, and we do it over and over again. And so now this is one figure here. And it's a one figure that's made up of 4 plots, and they'll all appear together in your little right-hand panel in RStudio. So this is nice because it means you can tie stuff together into one plot or one figure. But you can also, like, that wasn't very efficient. So what you can do is do things like this. You start to plot, but you start plotting using for loops. Okay. So if you remember with the for loop, we're going to say for, and in the parentheses, we're going to say I in 1 to 4. So that means we're going to execute the code 4 times, and I is going to be equal to the value of 1, then 2, then 3, then 4. And the code it's going to execute is hist. And it's going to specifically subset out of the column of express. And the column is going to be whatever the value of I is in that iteration. So in this case, we're going to iterate through, and it's going to plot, 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 plot. And you can do similar things so that you can update the main, so you can update the title and things like that. So it will do it super efficiently for you. So par is actually an incredibly powerful function. It has a lot of parameters in it. You can do things like change the size of the plot margins, the spacing between different elements, and the dimensions of the whole plot. Okay, but this can really get into like really fine tuning what the plot looks like. But a lot of the times people find it easier, especially when they're getting started, to just export their plot, put it into a PDF, and then put it into Illustrator or something like that to edit. And so we have a couple other customizations that we can talk about real quick. You can add text really easily using the text function. Okay, and so when you use the text function, what you need to do is just provide a position. So here we're providing a position, an X and a Y, so 20 and 60. You say what the text you want it to be. This is my plot. And then you can add things like color. And there are some font options as well, but they're quite limited. You can also use the data itself. So this right here, this is, I want one specific text output in one specific place, but you can add vectors. And so this is quite often used to actually label data points. And so here we're saying we want text and we want it to be at the control by the treatment, okay, which is what we used in this plot to generate this plot. Okay, so this text is going to follow the data points. And we're going to say we want to label it with the letters 1 through 6. So that means it's going to be the A, B, C, D, E, F. And then you can add this argument, okay? And so this is the really nice one if you want to label data points, because it means it doesn't just plot the text right on top of the data points. So it's not going to plot them exactly at control and treatment. It's going to add an adjustment of -1. So that actually puts it up slightly. And then you can change the color, of course, as well. So this text function is really a nice way to add custom text if you want to highlight, say, a specific point, or you want to highlight several points together and add some labels to them. Maybe you want to add the gene symbols for things that are significant or something like that. The big thing to remember with a lot of this, which is something that it took me a little while to realize and figure out, is if your text at any point is overlapping with the margin, it will not display. Okay, and so you can see that with F. F is not visible. So anything outside of this box that is part of the plot gets hidden. And so if you ever want to use text outside of this square, you have to use M text instead. So that stands for margin text. You can add custom lines. So this is good for like lines of best fit. If you want to add an XY to your XY plot, you can do. And it follows a very simple pattern for linear relationships. So there's kind of two ways to draw it. If you want just a straight line with a straight horizontal line or a straight vertical line, you can use the argument h or v supplied to the function AB line. And what h does is it says, I want a horizontal line at 10. So this is our blue line here. While v says, I want a vertical line, and it's going to be red. It's going to be here. However, if you supply A and B as arguments to the AB line, this instead allows you to draw diagonals, and what you're supplying is the intercept and the slope. So it's like y equals mx plus c. So here we have A, which is the intercept, which is so your gradient, and B is your slope. No, yeah. A is your intercept, so where it's crossing the line. Sorry, that isn't your gradient, it's your intercept. And B is the slope, so that's your gradient. So here we have a gradient of 1 and it's crossing over at 0. Okay. I think this is the last thing we can add to plots. Can we put a regression line? Yeah, so there's statistical ways to calculate regression, but if you calculate what your regression is, and from your regression you get the gradient and the intercept, then you can just add it in with the AB line for sure. But there are packages that you might use to calculate regression that will just draw the lines for you anyway. So there's lots of different ways to do this because it's quite a simple statistical method. There are actually several packages that do it, and each of them have different pros and cons. But yeah, it's one of those things where you'll play around and you'll find the one that you like. Okay, so yeah, like I was saying, the last thing is adding shapes. So sometimes you want to highlight a region of a plot that is of interest to you. And that's really straightforward to do with the polygon function. And all the polygon function is doing is saying, these are the vertexes that I care about. And so you supply a a vector of x coordinates and a vector of y coordinates. Okay, and so this one, this means 50, 50. So this is this point here. We have 50, 80. So that's going to be this point here. Okay, it doesn't have to be a square. It could be whatever you want it to be. But you're directly coding where you want the shape to be. And then you can add in color, density. So I did a density. So this gives it a hash approach. But there's other styles if you look up density. Okay. So the last thing we'll cover is saving your plots. Okay, so you may have seen, or you may have already done this, there is a button in your RStudio that allows you to just export. And so you can save it, you can copy to clipboard, you can save as a PDF. This is great, but it isn't the most reproducible way of doing things. Your plot is not tied to your code anymore. There's no evidence in your code where and when you exported your plot, even. So if you then have to edit that plot later on, you're not entirely sure where it came from. So at least the first step you can do is at least have evidence in your code. And so to export plots using your code through the console, what you have to do, my touchpad is a little sensitive. What you have to do is use one of these functions, okay? And so there's things like BMP or JPEG, functions which are basically saying, I want to create a BMP file. You give it the file name. So this will be a directory. You say you can add parameters such as what size you want it, what the units will be for this sizing, and things like that to control the resolution of your output. And then once you've done that, you use the function dev.off. Okay. So this is important because this first step is saying, I am creating a file. I want, instead of the plotting I'm doing to go to the console where I can see it, I want it to go into the save file. And then you can have all these different steps, right? You saw the plot we made earlier. We had 7 or 8 steps. So you could do these 7 or 8 steps. And then when you're happy and you're finished, you say dev.off, and it knows that you're going to close that connection. You're not going to be writing to the file anymore. The file gets saved, and then you can look at the file. Okay, so it's a very kind of disjointed way of just saying, switch the focus of the R plotting to somewhere that's very specific, and then you can switch it back to your console afterwards. So this is the example for BMP. You can see it can just do it. As long as you tell it where you want to save it, the rest is superfluous. It has some default values for resolution and things like that, but they add extra control. But yeah, this is a bitmap format. There's a JPEG function, PostScript. There's a lot of these functions. The ones I often use are PNG, because PNG is a nice data format for basically pixelated data, not vector-based data. But I use PNG, but then the one I use more than PNG is PDF, okay? And so the nice thing about PDF is it's vector-based, so that means you're not saving, you're saving the coordinates of everything, as opposed to saying, hey, this is a pixel and it's this color, and then this is a pixel and this is this color. That means there isn't really a resolution issue, and you can then go into the image, open it up later, and start making it bigger, and it should scale with that. Because all it's remembering is the coordinates as opposed to the pixels. The other nice thing about PDFs is you can then easily open them up in things like Adobe Illustrator or Inkscape, which is an open source and free version, essentially, of Adobe Illustrator. And then because it's saving all these different elements, you can then easily customize them yourself. So you can interact with them and say you decide you don't like one of the colors, or you get feedback from from your paper submission that one of the colors doesn't look right. You can then just go in really easily, highlight that object and change the color. Yeah, so PDF, super great. Okay, so there's linked to some exercises here. We have links to the fundamentals of data visualization, which I showed you. I will quickly show you this link because it's really good. So we're going to get into ggplot in a little bit. And so this has examples for ggplot, but it also has examples for base plot. So I often come here if I'm doing a new data plot that I haven't done before, or it's been a while, and say I want to draw a density plot. This one doesn't have an option. Okay, let me go back. Let me find a better option. Box plot. And so you'll see there's options for ggplot, and then there's options for basic R. And so then you can look at one you like the look of. Say I like the look of this. And it has all the code associated with it. So then you can then borrow this code and create a plot that is in this image. Okay, so this one has a jitter on top of it. So you can actually see the data points as well as the box plot itself. It also has caveats like this. This is really good information to know. As you start to learn about data visualization, you get to learn about caveats associated with different data visualizations. So box plot is actually, it's not the best visualization tool. You're much better to use something like a violin plot. Okay, because then you can actually see the distribution a lot better. Okay, so as I said, this has options in ggplot, and it also has options in base R. And we'll start to get into ggplot after this break. I have a quick poll to finish off the session today, or the base plot session. So I'm just launching that now. You can tell me which ones are true. Okay, we'll do 10 more seconds. Okay. So it seems that most of you got par correctly. So par allows you to lay out several plots. It also allows you to do a whole ton of different parameter customizations. And really that is where you'll find, oh, sure, sorry, there you go. Thanks, Amichai. Yeah, so par, everyone got this right pretty much or close to. And so this is where you'll find, if you do question mark par, that's where you'll find the most of the graph customization options. Okay. The first one tricked a few people. So it doesn't control the axis limits. So axis limits is controlled by Y lim and X lim. What breaks is controlling is the number of bins that you can put your histogram into. Okay. It's a really important argument to remember. And it's the main one you'll be using with histograms. Text is a tricky one because it does allow you to put text almost anywhere, the exclusion being margins. Okay, and so if you remember, M text is needed if you want to go into the margin area. And then lastly, the main argument is for plot titles. Yeah, so this is also true. I think it's about 50-50 whether you put this or not. So the main argument is the one used to add plot title. I'm not sure why they couldn't just say title. That would make more sense to me, but pretty much every single plot that you'll do, if you put main in, it will add the title. Okay, so that is us done for now. I'm going to be around if anyone needs to ask questions, confusions about yesterday or today, exercises, whatever you want to ask me. We will restart at 1, and we're going to be talking about ggplot. And this is really the first start to look into what tidyverse has to offer. If you are not sure what tidyverse is, do not worry. You'll know all about it soon enough. And it's a very useful set of tools that just makes your life a little bit easier a lot of the time.